Today's video is about modular arithmetic, and it's something that's kind of cool because you can understand it whether you're in elementary school or an adult, and there's some kind of cool stuff related to it. But most people haven't heard about it before. So recently I was learning a little bit of computer programming, and the book was really good on explaining most things, but then when it explained the operations that you can do with math stuff in the computer program, its definition for modulus was really confusing. I thought no one who doesn't already know what a modulus is, or modular arithmetic is going to understand what it's saying. So I thought I'll make a video explaining it for you guys. So this is basically based off of the definition the book gave. A divided by B with C remaining. For example, 100 divided by 16 with 4 remaining. The result of the modulus is the C part, or the remaining part. And if you're like me, you probably think that doesn't really make sense. So here I'm going to explain to you what they're trying to say, the guy that wrote that book. So basically, what it was saying with 100 divided by 16, 100 divided by 16, well, 16 goes into 100 6 times. 16 times 6 is 96, which would leave 4 left over. So basically, 100 equals 16 times 4, or times 6, with 4 left over. Or to write it with division, 100 divided by 16 equals 6 plus 4 sixteenths, or you could just put 6 and 4 sixteenths. And of course that could reduce to 6 and 1 fourth. But some of my students actually are in the habit, I guess one of their teachers told them at some point to do it this way. If they were dividing 100 divided by 16, whether it's like that or 100 divided by 16, they'll write it like this, 6R4. And I always try to get them to write it like that instead as a fraction. But actually, when you're doing modular arithmetic, this is pretty handy because the 4 is what matters, the remainder, the part that's left over. So how you'd write that is 100 modulo 16 equals 4. So you don't care about the 6 at all, you just care about the leftover part, the 4. So let's say you're wanting to do 27 mod 5. 5 into 27, 5 goes into 27 5 times, and then there's 2 left over, so that would be 2. And I'm going to show you in a second the way I think of it that helps it make a little more sense to me. But basically it's the remainder part that's left over is what that definition was trying to say. So you divide the number by the modulus, and then whatever's left over, that number, the remainder, is the value. So a couple things before we go on though. The remainder definition doesn't really work with negative numbers. And negative numbers are actually pretty easy. I'll show you guys that in a minute. But the other thing is you don't usually use modular arithmetic unless it's integers. So you wouldn't do 2.7 mod 2 or 17 and a third mod 5. No decimals or fractions, no pi, or no this number can't be a decimal or fraction either. Can't do 8 mod pi. Okay, none of that. You could invent different versions that would work with decimals and fractions, but I'm sure people have. But normally you're just talking about integers, so 3, 4, 5 whole numbers basically is what some people call them, but integers. So here's the way I think about it that I think makes the most sense. Let's say you're doing 37 mod 5. What I normally just think of it as is you keep subtracting 5 until there aren't 5 more to subtract. So you do 37 minus 5 is 32. Subtract 5 again, you get 27, 22, 17, and then subtract 5 again, you get 12, subtract 5 again, you get 7, subtract 5 again, you get 2, and if you subtract 5 one more time, you get into the negative numbers, so you stop at 2. So this equals 2. And 56 mod 11, 56, you can subtract 11, that will be 45, subtract 11 again, that will be 34, 23, 12, subtract 11 one more time, and it's 1. 1 is what's left over. Or if you are smart, you're probably thinking, oh, you can do 11 times 5 is 55, so you can just subtract the highest multiple of 11 that you can take away from 56 and leave a positive number, and that gives you the result. So 76 mod 10, subtract 10 7 times, that will leave you with 6. So that's how I like to think of it. Just subtract this number here, which is called the modulus, and that will give you, and keep subtracting it till you got a number that's less than that number. And that works for all positive numbers. Negative numbers work a little bit differently. So 37 modulo 5 equals 2, or you just usually say mod 5. But the full name would be 37 modulo 5 equals 2. Okay, negative numbers work a little bit differently. So negative 21 mod 10, since it's starting in the negatives, instead of subtracting 10, you want to add 10 until you get a number that is 0 or larger. So if you start with negative 21, add 10, that's negative 11, add 10 again, that's negative 1, add 10 again, and you will get 9. So this would equal 9. And negative 12 mod 5, you just add 5 a few times, which basically I'm just going to add 15 as a shortcut. That equals 3. So add 5 3 times. That's how much it takes. We'll do it the long way. Negative 12 plus 5 would be negative 7, plus 5 would be negative 2, plus 5 would be 3. And there you stop. Negative 6 mod 4, negative 6, if you add 4 would be negative 2, add 4 again would be positive 2. So that's 2. So if you have a negative number, add the modulus repeatedly until you get to 0 or a positive number, and stop at the first one you get to. If it's a positive number that is greater or equal to the modulus, then subtract it until you get to a number that's lower than that. So if you want to pause the video for a second, I'm not going to go over this, but I think it'd be interesting for you to think about what would happen with modulo 2 and modulo 1. So play around with that a little bit, or maybe just make up some examples, try it on your own for a minute. Okay, the most common example that you see if you look at this up online or whatever for modular arithmetic is a clock. And it's a really good example to help you kind of get the idea. So, for instance, what is the time 10 hours after 9 o'clock? So you're going to start at 9 o'clock, and you're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's going to be 7 o'clock. And the modular arithmetic that would correspond to that would be 9 plus 10 mod 12 equals 7. What about this one? 24 hours after 3 o'clock. So if you start at, it's 3 o'clock, and 12 hours later, it'd be 3 o'clock again. 12 more hours, you're back to 3 o'clock. So 24 hours after 3 o'clock is 3 o'clock. And you could say 3 plus 24 mod 12 equals 3. 25 hours after 4 o'clock. So if you start at 4, you go 12 hours, 24 hours, 1 more hour, you'd be at 5 o'clock. And if you want, you can pause and try to write it like this. And I'll tell you what it is now. It is 4 plus 25 modulo 12 is 5. This one, I'm just going to leave for you to do on your own. Okay, so if you played around a little with stuff a little bit earlier, you might be, or you're just thinking, this is weird. You might be thinking, so this is really strange that numbers are equivalent that shouldn't be. Like in mod 5, 6 plus 7 is 3? What? Like normal math, that doesn't really make sense, right? Or in mod 6, 7 equals 1. Or actually, put that to remind myself, you could say 7 equals 1, 7 equals 13, 7 equals 19, 7 equals 37. All these numbers are equal, right? And in mod 10, 100 equals 0. This seems really weird. Is math not true, the math you learned before, or is the rules just arbitrary? No, so technically, a mathematician wouldn't really write it like this. What they would say is 6 plus 7 is congruent to 3 in mod 5. So, and even if they wrote it like this, if someone wrote it like that, if you're talking about modular arithmetic, you're talking about something different. So it's just a matter of definitions here. So in modular arithmetic, yeah, 6 plus 7 is basically the same as 3. All these numbers are equivalent in mod 6, but it's not saying 7 equals 13 in general, right? It's saying in this sort of cyclic system where it repeats after you get to a certain number. So, like a clock, right? So some things in real life do repeat in a cycle, and those things this will work for. But it's not the same as saying this equals this. It's saying in mod 5, those are equivalent, or it's at the same place on the clock, basically. So there's one thing on that clock, the one we were looking at earlier, that technically wasn't right if we're talking about modular arithmetic, because this would be mod 12. Technically, this 12 should be a 0. So in mod 12, the only values you would get would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But you wouldn't actually use 12. So 12 mod 12 would actually be 0. Or the other way that I was just talking about, you could say 12 is congruent to 0 in mod 12. But anyway, so this one here, I put a 0. So this is mod 8. And we're going to do a few examples really quick. 2 minus 6 in mod 8. What is that? So if you start at 2 and you go down 6. So you're going backwards or down. 1, 2, 3, 4, 5, 6. That would be 4. Or the technical way to write that would be mod 8. Running out of room there. So 17, well, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That would be congruent to 1. That was at 1, right? In mod 8. So this notation, when you're doing the congruent thing, that a whole bunch of different things are congruent based on the modulus, you put a parentheses around that part. So if you're writing equal, you'd say 17 mod 8 equals 1. But this is that mathematician kind of way of writing it. So 7, 8, 9, 10, 11, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that was 1. Okay, 3 plus 9. Just start at 3, go up by 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be 4. And 10, 7, 8, 9, 10. That would be 2. Okay, so maybe stop and try some examples on your own. Maybe draw your own, write some out. So one other way of thinking about it would be with a number line. So I'm going to talk about mod 4 now. So in mod 4, 0 is 0, 1 is 1, it's less than 4, right? 2 is 2, 3 is 3. When you get to 4, subtract 4, it's 0. 5 minus 4 is 1. 6 minus 4 is 2. 7 minus 4 is 3. 8 minus 4 is 0. 9, you can subtract 2 4s, and that would be 1, and it keeps going like that. Negative 1 plus 4 would be 3. Negative 2 plus 4 would be 2, and yeah, it just keeps going that same pattern. So in mod 4, 7 is congruent to 3, negative 5 is congruent to 3, negative 9 is congruent to 3, 3 is congruent to 3, obviously. 67 is congruent to 3 because 64 is divisible by 4, and then so 67 would be 3. So there's an infinite number of integers that are all congruent to 3 in mod 4, or in any modulus, unless it's 2 or 3 or 1 or something like that. Okay, so here I'm just going to leave this for you to do on your own. Calculate those, try that out. And so next time I'm going to actually do a video, or sometime in the next week at least, I'm going to do a video showing a real life application of using modular arithmetic. Thanks for watching the video, and stay tuned for that next video.